So yeah, it's about time we've talked about the three-body problem. Not the TV show, not the book, the actual problem. What exactly is it? Why is it sort of unsolvable, or is it actually solved already? And does it make any sense in that TV show that's basically trending on Netflix? And so, hello wonderful person, this is Anton. Today we're going to discuss the three-body problem as the actual scientific problem, talk about how it makes or doesn't make sense in that TV show / the book, but most importantly, discuss the actual physical reality of whether it's possible and whether these systems exist out there. And as you can see right behind me, one of these multi-body systems just basically got destroyed. And that's in essence the problem with so-called n-body problems. A mathematical problem in astrodynamics that in essence tried to see if it's possible to predict the motions of various multiple bodies around some kind of a central point. And in short, the answer is not really. But a much longer answer is yeah, kind of, but only in some special cases. And so let's discuss this in a little bit more detail, but first a bit of a warning. There might be some spoilers for the TV show / the book The Three-Body Problem by Liu Cixin, which is basically the main reason I'm even making this video. But these spoilers are going to be super minute, and you probably already know what they are, even if you didn't watch the show or if you didn't read the books. And let's actually get all of them out of the way right now. Okay, if you want to skip this part, it starts right now. 3, 2, 1, let's go. So there's aliens that are coming to Earth from a nearby system of Alpha Centauri. And the reason they're coming is maybe not a good one. They basically want our planet. And the reason they don't like their own planet is because it's in a three-body system, which is perfectly illustrated right here. You have three bodies in a somewhat chaotic motion around one another, whose motion is somewhat difficult to predict and to describe mathematically. But interestingly, if this is just two bodies, it all becomes super clear. As a matter of fact, the two-body problem was one of the major reasons for calculus and was solved by Newton in his Philosophia Naturalis Principia Mathematica back in 1687. And that's of course the problem of bodies orbiting other bodies. For example, Earth orbiting the Sun. Although technically it wasn't just Newton, it was also Johannes Kepler. But they quickly realized that once the third body enters the equation, that's when things get really complicated. And it wasn't until the 19th century that various mathematicians, including the French Henri Poincaré, officially declared that it might be unsolvable. Kind of. Or at least there's no general solution, just like with two-body problem. And in Universe Sandbox, if you have that application, there's even a simulation called Random Three-Body Problems. And it basically always starts with 3 stars in random orbits. And as soon as you start the simulation, things get chaotic pretty quickly and usually ends up with the same scenario. You're going to see it very, very quickly. And so here, 2 stars assume an orbit around one another, and the third star either starts orbiting around them or very often gets kicked out. Here, if we run this again, you'll see how it's quite likely that one of the stars, there it goes, gets kicked out, whereas the other 2 remain in orbit as a binary system. And that's essentially what happens with most actual three-body problems out there in space. Because they're unstable by nature, they always end up in a destroyed system at the end. And that's because individual differences in their orbits get amplified really, really quickly and lead to extremely unstable behavior that's somewhat difficult to predict. Now you can actually run this many times and you'll pretty much never end up with a stable system that lasts for longer than a few hundred years. But how is it that we then have multiple star systems out there, and even star systems with 6, 7, or 8 stars? Well, in like 99.999% of the cases, it's always the same way. Astronomers refer to these as hierarchical systems. It's always a star orbiting another star, and then sometimes a binary orbiting another binary. And you can actually have different types of multiplicities, resulting in different types of orbit. Here's actually an example of a non-tuple or 9-star system known as QZ Carina. And here's an illustration of a typical quadruple system, where essentially you have 2 binaries, with each of the binaries orbiting the other. And in this case, these systems do become relatively stable, but these are not examples of three-body problem. As a matter of fact, nature found a way to solve the three-body problem by turning it into a multiplicity of two-body problems, which is maybe what's happening here as well. You have a binary in the middle, and then you have another star orbiting the binary. So even though this is a triple star system, it is no longer a three-body system. But in the book or in the TV show, those aliens living around the triple star system, seem to live in a true three-body system that's essentially causing their planet to experience unpredictable climate changes, going between being super hot or super cold, or sometimes experiencing other extreme effects. But the only problem here is that in the book, the author chose Alpha Centauri system, which technically is a triple star system, but as you can see right here, it's not a three-body system. It's once again a hierarchical or multiplicity star system with Proxima Centauri in orbit around a binary, Alpha Centauri A and Alpha Centauri B, which are in a relatively permanent orbit around one another. And so here, if there are any planets, and we so far only know of planets around Proxima Centauri and not Alpha Centauri, these planets do have a chance to have relatively stable orbits in certain locations around these stars. But these types of planets are now referred to as circumbinary planets and experience entirely different problems. Some of the videos from before in the description below provide a little bit more information. But in a nutshell, a typical binary star system that contains circumbinary planets will only have a certain region around it where stable orbits can exist. Anything inside will be unstable, with planets basically getting kicked out, and any planets that do exist here will have to follow an extremely precise motion around the star system. These have been actually discovered, and we know of a few of them, but nowadays scientists refer to them as Tatooine planets, after the planet in Star Wars. And so in this case, the author behind the book actually didn't really choose the appropriate star system to try to express his ideas. But in terms of science, there's a much bigger shortcoming in the story. And here it's actually in regards to that alien life living on those planets. Okay, so assuming that they managed to evolve, and assuming that they possibly took at least a few 100 million years to get where they are, that by itself is already basically kind of science fiction. As you can see from these simulations, none of these star systems can last that long. They fall apart within just a few hundred years, maybe a few thousand years. For them to last millions of years in order to allow for complex life to evolve, yeah, that would be extremely unlikely. But is it impossible? Well, not really. As a matter of fact, now, let's talk about a few cases of actual star systems out there that we know have these three-body problems going on inside of them, and a few studies that did work out the average age for these star systems before they completely fall apart. But first, just a little bit more math. So even though in the book and in the TV show, they pretty confidently state that it's impossible to solve the three-body problem, that's not correct. It is solvable, and it has quite a lot of solutions, they're just not general solutions. A much more appropriate way of saying it would be, it has no general solution that you can apply to every situation, but there are plenty of special cases. And I actually wanted to start with that. So first of all, you can technically solve this statistically, and there are also different analytical solutions that involve series that can actually predict the approximate time for the system to fall apart and the most likely state for each of these objects eventually. So basically, are they going to end up completely by themselves in a binary orbit and so on. But on top of this, there are physical solutions for various special cases. Here's probably the most famous one, a figure 8 solution to the three-body problem. And so here, these three objects are in a orbit around one another, and this is a permanent orbit. It technically will not break unless there's a fourth object, such as a tiny planet, that can eventually disrupt their orbit and thus introduces more chaos, breaking the system. Here's a bunch more solutions. All of these are special solutions to the same problem discovered in the last few decades, mostly using supercomputers. But it's really in the last few years, actually since the publication of the book, that a lot of mathematicians started to find more and more solutions, with the actual number increasing exponentially. For example, by 2017, Chinese mathematicians, possibly inspired by the book, I guess, discovered approximately 1,000 solutions by simulating 16 million different systems. But it only took a few more years for the Bulgarian scientists to discover even more. This was the last paper about this topic, and here they found over 12,000 different specific solutions, each of them providing individual solutions to various three bodies. Although the problem in this case is that these 12,000 solutions were all for bodies of the same mass. If the mass changes just a little bit, none of these solutions work anymore. So once again, a very special case. Which also probably means that none of these systems truly exist anywhere out there. We're unlikely to find three stars with exactly the same masses, so none of these solutions would apply anyway. But that's the math behind this. How about actual physical evidence? Well, there we do have actual observations, and in this case, many observations from the last few decades. And in astronomy, these systems have a name. They're known as the Trapezium type. named after the iconic Trapezium cluster in the Orion Nebula. And so here you have a multiple star system where there is no hierarchical arrangement. So in other words, there is a 3 or technically n-body problem that will usually result in a system eventually breaking apart. As a kind of a side note, I was recently working on a slightly different video, mostly about rogue planets and various binary systems. And the scientists are always surprised they find so many different rogue planets out there, which are basically traveling completely by themselves. And in quite a lot of those cases, those planets were very likely kicked out of the system, once again because of the n-body problem. Likewise, a separate study from just a few weeks ago discovered that various blue supergiant stars can sometimes be formed when two smaller stars merge together. And these types of mergers are actually another solution to a 3-body problem. It basically implies that in some cases, something destabilizes the system with two stars colliding, forming something larger. And a few of these have been discovered in the Milky Way. But that's how these n-body problems usually end. What about the ones that still exist out there? Well, outside of certain regions in a galaxy, you're actually extremely unlikely to find any of these trapezium systems because of this instability issue. But we can find them in various molecular clouds where new stars are forming and start orbiting in these chaotic motions. And at least one of the studies you can find in the description, completely unrelated to the book or the TV show, was able to analyze some of this back in 2008. At first they discovered 968 such systems in the Milky Way, but by thoroughly analyzing each of them, they realized that only 14 were true trapezium. Or basically most of them appeared as trapezium systems, but were actually hierarchical, or were not even related at all with stars in different star systems. Yet 14 were definitely confirmed to exist, and they appear to be true trapezium systems. But all of them contained relatively massive and extremely bright stars, usually B-type. These are of course really bright, really massive stars that usually only last for a few million years. And of all of these 14 systems, the maximum age for all of the stars was only 50 million years. And that's not actually a lot, with the majority very likely falling apart within just a few million years, resulting in a binary and a single star, or even 3 single stars, traveling by themselves. But even the distance between these various stars was relatively large. The mean radius here was at least half a light year, so these were not stars orbiting next to each other at all. And this is the only reason they were able to maintain orbits for millions of years. If they were much closer, they would most likely fall apart much quicker. And so if we focus on the TV show again, or on the book, in that TV show, these species here, realistically speaking, would not have much time to evolve at all. For example, in our own solar system, after 50 million years, the Earth was still super hot and it just finished forming the Moon. And as far as we know, it took at least a few hundred million years for first life to start appearing. And here we're talking about primitive life, not life with advanced technology. Although even more interestingly, in that particular study, they also identified the closest such system to us, and it's not in the Orion belt, it's not Trapezium. It's actually inside this beautiful cluster known as the Pac-Man Nebula, more officially known as IC 1590. It's about 3.5 million years old, and it's almost 10,000 light years away from planet Earth. And so here we actually have a very interesting system with an n-body configuration, because there are actually 5 stars, not just 3. Although technically it represents 2 binary systems and a 5th star that forms that 3-body pattern. And so in reality, even here things are a little bit more complicated. And so in a nutshell, that's pretty much it. 3-body problem is definitely complex, but not impossible. And though it does exist out there, it's never really permanent and almost always ends up producing more stable binary systems in some kind of a hierarchical arrangement. And normally we can only find these in various types of star nurseries, because these systems don't last for longer than 50 million years, at least based on observations from the Milky Way. And so can these star systems have planets with maybe life on them? Extremely unlikely. Because first of all, it would be impossible for these planets to even form, and that's because in order to form a planet, you first need to have some kind of a stable planetary disk, like the ones you see right here, and if those planets were captured from somewhere else, which is a possibility, they would still not have stable enough orbits to survive for longer than, once again, maybe 50 million years, but most likely much shorter. And so even though it's still a cool science fiction story, and definitely a really cool concept, in reality things are maybe just a little bit different from how they were presented in the show. But on that note, that's just the first part I wanted to make about this, because we're also going to discuss some of the other scientific concepts from the book and from the TV show in some of the future parts. And the dark forest hypothesis you can actually learn more about in one of the videos in the description. Anyway, on that note, thank you for watching, subscribe, share this with someone who loves learning about space and sciences, come back tomorrow to learn something else, support this channel on Patreon by joining the channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.